¿Dónde estamos? Esto.
Professor Bernabe, you can start.
I can start?
Yes,
okay.
please.
Okay, I was just waiting some indication. Then wait a minute. Good morning to everybody. Let me sometimes to share my display. Wait a minute. Well, please let me know. Are you seeing my display, my screen? Then, good morning to everybody. Good afternoon. Here in Valencia is good morning. So I would like to thank the organizer of this international seminar on sustainable technology in modern energy, with this very attractive title. And well, the title of my talk is Smart Material for Solar Energy and Hydrogen Production. So I'm Professor Bernard Marie Sucas. I work at the Applied Physics Department at the Universidad Politécnica de Valencia in Spain. Here, I like to show you where is Spain. Spain is here in the middle of this map. Here is my city, more or less 500 kilometers from, wait a minute, 500 kilometers from Pakistan, from Islamabad. Well, these are some images of my city. We are very good at cooking paella, which is our national dish. We are very good also growing oranges. Well, well, the subject of this seminar is mainly based on the solar energy. If we deserve, it is clear that we deserve a green feature, and well, the only possibility is change the way we produce our energy. So we have to use necessarily solar energy because it is clean energy and very respectful with the ambient, and is distributed all over the world. As you know, the electricity produced by this kind of devices, like the photovoltaics, can be used directly, can be stored in batteries or in hydrogen, or can also fed into the existing electricity grid. And as you know, the light emitted by the sun and falling on Earth is about 1.5 10 to the 22 joules, which is more or less 10 to the 4 times the daily energy consumed by humanity. Here you have the minute I like to. Here you have what is on the scale, what is the terrestrial sunlight, the energy supplied by the sun and heating the earth, and the global demand of the humanity is 10 to the minus 4 times the energy of the sun heating the present PV installation is quite slow right now. Well, since this is the distribution of the primary energy production in the world. In 1965, 90% of the production came from fossil fuels, oil, coal, and natural gas. And 35 years later, right now, we are still consuming 87% of fossil fuels. Is in the last 5 years, here you have the global energy consumption in the last 20 years, and it's only in the last 5 years when the fossil fuels, coal, oil, natural gas, start to decrease slowly, and all the renewables increase yearly. Well, so the renewable energy sources, as you know, are mainly photovoltaics, wind, and hydropower. The nuclear, well, nuclear is, there are some controversy with nuclear. Mainly in Europe, some countries have declared nuclear as a green source, but other countries disagree with that. So it depends on the policy of each country. Well, if we want to use efficiently the green power sources, we require produce electricity, but also storage the electricity. In order to storage the electrical energy, we can use batteries. At present, the best performance lithium-based batteries, or we can use hydrogen. So hydrogen, we can produce hydrogen using electricity or light. You have to storage hydrogen, and later we can produce electricity by means of some process related to hydrogen. So hydrogen, I think, in my opinion, hydrogen is the hope for global usage of green energy. Well, here this slide shows the benchmark capital expenditure in photovoltaics in the last 10 years. As you see, the price decreases. This is mainly based on silicon, because the production, the cumulative installed solar photovoltaic capacity is increased. So the relation is as inverse as expected. Price decreases because the installation increases. Well, from the point of view of physics, wait a minute, sorry for this. Wait a minute. Let's remove that. Well, from the point of view of physics, then this slide shows the efficiency limits of photovoltaics as a function of the cost. This is the efficiency related to the cost. So in that slide, we can observe the three, what do you consider three three kinds of photovoltaic technology. One is, number one here, is the bulk silicon, which still is the king of this technology, the most abundant indeed. Number 2 is thin films. And number 3 is what is called third photovoltaic generation. So here we have also some limits established by the physics. For example, the Shockley-Quasar limit established that the maximum efficiency that can be attained by a semiconductor with only one gap is about 30%. But, well, if we concentrate the light more than one sun, then we can expand this limit up to nearly 68%. And the ultimate thermodynamic limit at 46,000 suns, what is unsavable, is near the 100%. Well, there are also a limit, what is the minimum balance of system, but this is related to the other components necessary for this photovoltaic installation, apart from the modules, apart from the solar panels. So there's a minimum, what is called the balance of system, and here we have the prices in US dollars per watt. So what we want in that graph is to go for low cost. We want to go low cost to go in that direction, and also high efficiency in that direction. So this is the interested part for us, which means use third photovoltaic generation. For using this kind of photovoltaics, there are several approaches. One is to use multi-junction solar cells. The second one is intermediate band devices, or use also a four-phase up and down conversion. And well, there are also a new of smart material, whatever the perovskite, that can be also very useful to attain this kind of this challenge. So here you have what is the difference. Sorry. Here you have how the fundamentals of the multi-junction or tandem system, which are mainly based in three-sheet material. It consists of 3 or more solar cells, stacked solar cells with different band gap, and the solar cells, the material with the higher band gap, absorb the higher energy photons, then the second, and then the low energy in the bottom. So with this technique, we can take advantage of the full sunlight spectrum. Another way to do that is to use materials, only one material, but with intermediate bands. So in that case, you are able to use below the band materials. For example, this kind of, here you have valence or conduction band with photons. We can promote electrons from the valence band to the conduction bands, but we can also use the below the band gap materials and then promote electrons for the valence band to the intermediate band, and then another photon can promote this electron to the conduction band. And the third way to increase the harvesting of photons is to use semiconductors, is to use four-phase conversion, up or down conversion. Here, which consists in, here we have in this graph what is the solar spectrum, and using suitable materials, we can modify the spectrum of the sun and feed the sun spectrum to the best to our materials. So in this slide shows the evolution of the efficiency of different kinds of solar cells. Crystalline silicon here in blue, thin film technologies in green, or multi-junction. The multi-junction already started in the 1980s, and now in 2005 they reach a limit of about 30% using system of 3 junctions. Well, this is the basic of this material. It uses multi-junction solar cells. The present technology allows to build system with 6 junctions, and well, this is a stack of junction of solar cells with different band gap. The top energy band gap in the top, another middle, and the lower band gap in the bottom. With this system, we are able to take advantage to use efficiently all the spectrum, all the sun spectrum. Well, to grow this kind of system, we have to use expensive techniques. With, for example, molecular beam epitaxy, which requires ultra-high vacuum and is not easy to manage, or methyl organic chemical vapor deposition. Methyl organic, this can be a little bit more commercial than MBE, but methyl organic are also dangerous. Well, the aspect of that is something like that. We produce this kind of system, work with solar cells very small, about 5 times 5 square millimeter, and they use concentration, the lens, to concentrate the light. For example, this example is concentrate 404. This system needs also to use track, because the system has to be always perpendicular to the sun. So it only can work from the parallel 40 to -40. So not all over the world, only in this zone of the parallels. And right now, well, this is how has the evolution of this kind of technology. In April 2011, they reached 43%, 46%, and 2 years ago, the limit is 47%, using systems 6 junction and 143% in concentration. This is the evolution. Well, the other approach is to use intermediate band solar cells, what is based on multi-energy level approach. Here, this is the system. We have a material with an intermediate band that the electrons from the valence band can be promoted to this band with below the gap, photons with energy below the band gap, and then again promote with another photons to the conduction band. So what happened with that is that we can use, the system can use infra gap botons with energy lower than the band gap. And well, the result is we can have a higher short circuit intensity, and also higher open circuit potential, because the open circuit potential VOC is proportional to the band gap. So as a result, we were able to increase the current and the open circuit voltage, so the power of our system can increase. Comparing with the multi-junction system, here you have on the left the multi-junction. Every junction absorbs one part of the sun spectrum of the photons. Well, the demonstrated efficiency now is about 47%, as I have mentioned. And when dealing with multi-band, well, you can use, theoretically, use only one intermediate band, or you can use n intermediate bands. So according to the theory, the efficiency can be up to 86% if we use a lot of intermediate bands. Well, theoretically this is possible, but in the practical, this is not easy to control the energy levels in a material. Well, the theory prediction for that is that this material, copper gallium sulfide doped with chrome, can be very useful for that. So we have worked on this approach by producing this material, copper gallium sulfide, by means of electrodeposition. With electrodeposition is a cheap technique, a very convenient for labs with a limited budget. No, so as work with sulfur is quite difficult, we have produced copper gallium selenide, which is more easy, and then proceed with sulfurization in molecular gas. So we produce by electrochemically copper gallium selenide, and then after a process of sulfurization, we obtain copper gallium sulfide. Here you have what happened. This is the case for copper indium selenide. When this material as electrodeposition is a low temperature technique, the crystals are not very good. So we need to the layers are not very crystalline. You see here in red, but after that salinization process, the peaks, the X-ray peaks increase a lot, which means that the material has been very well crystallized. And then the same material after suffering a sulfurization process, the peak shift will mean that we have substituted all the selenium by silicon. This system can also be seen if we represent the absorption coefficient as a function of this. No? For example, copper gallium selenide has a band gap about 1.66 electron volt, and after suffering a process of sulfurization, the band gap shifts to 2.2 electron volts because most of the selenium has converted to the sulfur. Why we use copper gallium sulfide instead of copper gallium selenide? Because the optimal gap for hosting an intermediate band is 2.3 electron volts. This is why we use sulfur is required. Well, then when doping with chromite, we observe the following. Here, this is normalized absorption on the right. This slide represents the absorbance as a function of wavelengths. After when the material is crystallized by electrodeposition, this is the absorbance of the copper gallium selenide. After sulfurization, the band gap shift, then the absorbance shift to the left, low wavelength, which means high energy. After stopping with chromite, you observe an absorption below the band gap, which is due to this intermediate band absorption. So here you have the schema, the energy schema we propose. The gap is 2.2. More or less, this band is centered in 1.6. So this is what we believe is the band structure of our material. Well, on the right, this slide shows the current, density current, the GB curve, density current as a function of the potential, and for different material, copper gallium sulfide, with different amounts of chromite. So as you see, as the chromite doping increase, the open voltage is the same, but the current, the short circuit current increases a lot. Which means that the photoconversion efficiency can change for 13% for this material without chromite to 34% with chromite. Well, this is from the point of view of theoretically, because this material, yes, in the practical is too resistive to be able to produce good solar cells. Well, another approach, as I mean, is the down conversion or up or down conversion. So that means we can change, we can using phosphor, we can move these photons on the, which are not profitable for the solar cells. So we can promote these photons to this zone by absorbing 2 photons and producing 1 photon of higher energy. This is what is called up conversion, or the higher energy photons can also be used in a material which is called a phosphor, which is called down conversion. We absorb 1 photon and we produce 2 photons in the suitable zone for the phosphor. So this energy below, in the case of silicon, the down conversion stands for 50% of the solar energy, and the photons on the upper conversion is 60%. Well, in the real devices, using this kind of materials, the PCE, the photoconversion efficiency, can improve 1%. Well, we have worked with this in this approach, both phosphor conversion and also intermediate band, in a European project called NanoThys project and funded by the European community. So we work with different universities in the world, Politécnica de Valencia, Politécnica de Madrid, one university in Chile, another in Mexico, and in Portugal, Warsaw University of Technology, and one university in India, who the Indian colleagues prepare the phosphors. Well, so as a summary, multi-junction solar cells require specific techniques and concentrators. The technology is quite expensive, but the efficiency, the record efficiency, is about 47%. In the case of intermediate band, well, theoretically, the predicted efficiency can be 67 or even 87%, but the devices are not demonstrated. So you add impurities. The reason is you add impurities to a better efficiency of collecting the photons, but these impurities impedes or hinder the normal transport of the carrier. So we have one effect which favors the efficiency, another who drops the efficiency. Well, on the unknown conversion technology, this is compatible with silicon-based technology, but up to now, well, 1% can be. The real devices has improved only 1%. Well, another approach to work on that is the hybrid perovskite materials, a kind of new materials called hybrid perovskite, which has a crystal structure similar to a mineral cation titanium oxide 3, ABX3, and well, due to their long diffusion lengths of charge carriers, the efficiency has increased a lot, more than 20% in only 5 years. Another interesting option, another characteristic is the processability of this material is low cost. So practically every laboratory in the world can process this kind of materials. And well, you have also a lot of possibility to prepare this kind of material because the material is prepared. We have one big cation called A, called the big cation. We usually use anorganic, can be methylammonium, ethylammonium, formamidinium. There are a lot of possibility to use as big cation. The structure has also a small cation. With a small cation, usually you can use lead, but also tin or germanium. And for the anion, we can use analyte. Analyte, it is iodine, bromide, or chloride, or a combination of every material. So what happened? Here you have what is the in 2015 the novelty for the efficiency of solar cells is that the appears for the first time the perovskite solar cell with a efficiency of 20%. Well, how we prepare this perovskite? In our lab in Valencia, we start 5 years ago to synthesize this kind of materials. So it's quite easy. We use methylammonium solvinetalone, and we mix this with one hydroallyl acid, hydrogen plus iodide bromide chloride. This mixture is stirred for 2 hours, and then we heat at 100 degrees, and we mix the solution with lead nitrate. So the results is, here you have what is the synthesis is described by this situation: methylammonium, hydroallyl acid, lead nitrate, and finally we have hybrid perovskite. So we are able to obtain powders, different colors depending on the composition of the powder. In that case, methylammonium with lead, iodide, bromide, or chloride. Or we can also produce thin films if we dissolve these powders into organic solvents like dimethyl formamide, dimethyl sulfoxide, and they, by spin coating or dipping, we deposit these materials on as thin films. Well, this slides of the absorbance of the materials as a function of the composition. So this is very interesting because it's quite easy to tanning the band gap for the energy we are interested. So this is the absorption, a function of energy. And here we have low energy band gap is the methylammonium lead iodide. High energy is methylammonium lead chloride. But we can mix, we can tune the band gap by mixing the halides. No, so it's quite easy to fix or to obtain the decile band gap. Well, the material, this kind of material also exhibit out very good photoluminescence, and this slide represents the photoluminescence density as a function of wavelengths. Again, we have low energy. The low energy is happen for the methylammonium lead iodide, and bromide is in the middle, and chloride is the high energy. And we mix the composition so we can obtain the emission in the ratio we are interested. Well, in order to build a perovskite solar cells, we have to build several layers. So the band energy schema of perovskite solar cells is we have the absorber is the perovskite. So the perovskite works as an absorber. It absorbs photons and produces electron hole pairs. Then the electron hole pair, the absorber is sandwiched between two layers. One layer is what is called electron transport layer, which is an N-type semiconductor, and the HTL is a hole transport layer, which is a P-type semiconductor. So the interest of that is the electron hole are producing the absorber. The electron is conducted to the ETL part, which is mainly full with electron. So the recombination here is very low, while the hole goes to the other part, to the HTL. So the possibility to extract the carriers from the solar cells is increases. There are two possibilities, what is called the normal and inverted setup for the solar cells. In the normal, we start the titanium oxide is the ETL, and the speed of, for example, the STL, and the inverted we start by the P-type, the perovskite, and then the HTL or N-type material. Well, here this slide shows what is the flow diagram for solar cell fabrication process, and we prepare this in our lab. And this is basically spin coating. So we have our sample here. We deposit the solution. The system is turning. Then we add some chlorobenzene, which is called anti-solvent, in order to control the crystallization. And then we heat a little bit, and we have also the perovskite. Well, for ETM, as electron transport layer, the best material are titanium oxide or zinc oxide. And for HTM, for hot transport material, what is a peptide semiconductor, we can use organic material like spiro or metal, or inorganic, like copper oxide, nickel oxide, or copper iodide. Well, here you have what is the FSM field electron scanning electron microscope image of this kind of devices. It's the substrate, zinc oxide, the absorber, and the spiro. Well, and well, we have also prepared this kind of samples and made numerical simulation by scabs in order to know what are the best conditions. So first thing we obtained was that the optimal thickness for the absorber is about 400 nanometers. And well, in 2017, we obtained, we calculated an efficiency of about 60% of maximum. And well, this fit very well with the record of experimental materials, experimental solar cell, which was 22 in 2017 or 25.5 right now. So our calculations are quite exact. Well, we have also worked with using alternative HTM. And in that case, we have made calculation with all these possibilities. Copper oxide, copper thiocyanide, etc. This is the results. The result means that the best material for us from the best material, or the HTM material able to produce the higher photoconversion efficiency is copper oxide. Here we have the different materials and what is the calculated efficiency. Theoretically calculated or experimental. Experimental, you see, for the spirometal, which is the more commonly used, it fits very well. From copper oxide, there are not yet materials or solar cells produced with this, using this HTM. Well, well, in our lab, this is the evolution of solar cells prepared in the Universidad Politécnica de Valencia. In 2015, our first solar cell delivered a performance of 3.77%. Next year, 2016, 11%, and in 17, we reached nearly 15%. We have, this is the aspect of our devices, and this slide shows the EV curve for different pixels, for different pixels, and the experimental and the theoretical curve of that. Well, at present, the record for perovskite solar cells is 25.7%. There is another option, which is tandem solar cells, which is made by perovskite solar on silicon, which is near 29-30%. And this is the present situation. Well, the advantage of the materials is that materials are cheap and attainable because the processes are done at low temperature. We have tuning the composition. We can use flexible substrates. It's also scalable, and the efficiency is very good. It's very, very good. Well, the drawbacks is, well, materials are very sensitive to humidity. They are unstable, and there are some phenomena of hysteresis which is not well understood. Well, what is our work for that? Our feature work. So we are now working on that. We have preparing mixed alloy perovskite by mixing, that can be mixing the alloys, iodide bromide or iodide chloride, etc. We are also doping with rubidium, cesium, formamidum in order to increase the stability. And we are also using inorganic perovskite instead of hybrid perovskite. Inorganic perovskite are mainly based on cesium. And cesium can also be doped with several materials, rubidium, lithium, chloride, etc. So what happened? Cesium lead iodide is metastable, so it degrades very rapidly. Cesium lead bromide 3, the band gap is too high, but the best option for us is cesium lead iodide 2 bromide. With the band gap is quite superior to solar cells. So in the future, so we are working on that, but also we are in the future we are going to work with another technique, with another processing technique, which is inject printing. So we are going to receive a new a full system which allow us to make inject printing technique, to use the inject printing technique. Our interest is to print perovskite layer and also photovoltaic and optoelectronic devices using this printer. Well, comparing with the silicon, the procedure to obtain perovskite solar cells is quite easy. So we mix the precursor with salt, with an organic solvent, and we have the perovskite liquid formulation. And then we have to deposit this on a roll-to-roll system of by spin quality, by the inkjet printing on a substrate, and then we are able to obtain solar cells, low-cost solar cells, and with good efficiency. So, as a conclusion, perovskite solar cells in 5 years has reached a record of 25%. The research on that materials are to use inorganic perovskite to improve stability, or to use alternative HTL like the lafosits or metal organic frames, or also use new deposition techniques like slow dye or inkjet printing. And well, due to the efficiency and simplicity of photovoltaic solar cells, these materials are attracting very much big labs and companies to produce perovskite photovoltaic modules with increasing performance. And let me, as a last part, I would like also to talk a little bit about hydrogen. The hydrogen is the hope for, well, in my opinion, is the hope for a zero-emission society. At present, the production of hydrogen comes from fossil fuels. 95% of hydrogen is produced by reforming petroleum and natural gas. This technique uses high temperature. If you use high temperature, the process is not very performant. High pressure also, and deliver a lot of CO2. Well, minor contribution comes from water electrolysis. Water electrolysis is produced right now more 4% of the industrial hydrogen, but is expected to increase in the next year, because most governments are interested in the development of this kind of energy vector of the hydrogen. Another option is use photocatalytic production of hydrogen. In that case, with electrolysis implies the use of electricity to split the water into oxygen and hydrogen, and photocatalytic hydrogen production absorbs. The idea is to produce the splitting of water by using photons. Well, here you have what is called solar to hydrogen mechanism. So we can use an electrolysis, which uses the electric potential to split the water molecules, or you can use photochemical processes, which are you use directly the light on the photocathode or photoanode, and then you produce also hydrogen. Well, right now the electrolyzers are commercially available. So right now you can purchase this type of electrolyzers, alkaline electrolyzers, proton exchange membrane electrolyzer or solid oxide electrolyzers. This is available in the market. The efficiency of this material or this system changes depending on the technology used. So it ranges from 42% to 70%. And what is much interesting is that the capacity is very scalable. So you can purchase a small system able to produce with the power of few kilovolts, or large system in the order of 100 megawatts. So these electrolyzers are in the market, and you can purchase the capacity you want. Well, for the case of photoelectrolysis, well, photoelectrolysis or photolysis, so what we do is using some materials alike, we produce per electron holes by means of hydrogen evolution reduction, oxygen evolution reduction, which are produced in the cathode and the anode. So we split the molecule of water into oxygen and hydrogen. And well, to do that, the energy required for each molecule is a photon of 1.2 electron volts. So right now, these techniques start to be operative using titanium oxide, but the titanium oxide has the band gap is very large. So the best, if you are able to use visible light, so you are able to use more efficiently the sun spectra, and well, between 1.8 and 2.2 electron volts is enough to produce the splitting of water. Well, we need materials to do that. In the beginning, the people started to work with titanium oxide, but the gap is 3.2. Only this material only use the UV part of the sun spectra. Wolframium oxide was also used, but like it's enough with 1.23 electron volts, so it's better to use material with a smaller gap than, for example, hematite, iron oxide. Well, another way to reduce the band gap of titanium is to dope with nitrogen, fluor, or phosphor, just to decrease the band gap and be able to absorb more photons. Well, the photoelectrochemical water splitting is based basically in semiconductor. So there are several possibilities. We can use mainly N-types photoanodes, or photonode photocathodes, or P-types, but everywhere are semiconductors. So the photoelectrochemical water splitting strategy are always based on semiconductor materials, semiconductor devices. Well, this slide represents the theoretical limit for solar to hydrogen efficiency. So in that, in some sense, this is similar to the Shockley-Quasar limit. So here it indicates the solar to hydrogen efficiency as a function of band gap. So if you decrease the band gap, then you are able to obtain to afford more photons and to split more water molecules. The limit is 1.23 electron volts. But here you see the oxide of titanium oxide, the limit is 1%. If you reduce the band gap using wolframium oxide 6%, and the limit for hematite is 15%. In our lab, we have also worked on that. So in our lab, we have produced hematite, chrome doped hematite for water splitting. Here you have some of the results. This slide represents the photocurrent as a function of time. So the photocurrent, if we increase the doping with chromite, so the photocurrent increases considerably. well, an option to increase the efficiency is to use nanostructured materials. If you are able to decrease the depletion ratio and the length, diffusion length is lower than the depletion ratio, then you are able to obtain all to extract the pairs electron hole from the material, and then use the carriers in the external system. Well, there are several strategies to produce tubes, nanotubes, etc. Well, and finally, this is what I think is going to have in the next year, at least in Europe. This is the system I expect. Well, here you have. This is an example of green hydrogen for a self-consumption in a house or in a community, no? In an energetic community. So here we have photovoltaic generator, produce electricity. With this electricity, you can use directly, consumers can use directly the photovoltaic generation, but you can also use this electricity to produce hydrogen with using an electrolyzer. So an electrolyzer needs water supply, electricity, and produce hydrogen. The hydrogen is stored. You want to efficiently store the hydrogen, you have to use a compressor. Compressor needs also electricity. Then you have a container, hydrogen container at some pressure. Then, when you need to produce electricity, so you have to use hydrogen fuel cells. Here you can one or several. And then the fuel cell use hydrogen, produce electricity, and it can be used by the consumers. But if you observe, this is a battery. This behaves as a battery. But in that case, the battery, this system, the advantage of that is that is scalable. So you can store kilowatts hour or megawatts hour, because both the electrolyzer and the fuel cell at present, right now, you can purchase the size you want, from kilowatt to megawatt or 100 megawatt. The same for the fuel cells. Well, what I expect is going to happen in the next decade. So the photovoltaic generation now are mainly silicon, but in the future is, I think, perovskite will be some place in that, in the generation of electricity. And further, the electrolyze in the future will be substituted by photoelectrochemical generator. Well, so this is the end of my talk. A carbon-free society requires renewable energy. What are solar, wind, and hydropower for direct use, but it is necessary to use hydrogen as energy vector. So, involved technology to be improved related to green hydrogen in the production of green hydrogen, but also in the fuel cell technologies to convert hydrogen into electricity. The electrolysis technology is enough matter to be commercial. Right now it's commercial, and the photoelectrolysis is still under development. Well, suitable materials for photoelectrolysis are III-V semiconductor, perovskite, delafosides, iron oxide, etc. And that's all. Thank you for your attention. I have some slide of my city. This is my city, Valencia, and this is the campus of the university, which is beside the Mediterranean Sea. Okay, thank you very much for your attention. Do you have any question?
It is Professor Dr. Lai Khan, Chairperson ComSets, ECE Department. Thank you very much, sir, for a very detailed and a very good presentation. I have just a very small question. That is, on one of your slides, you showed that the perovskite enjoys the tunability. As you said, that the tunability is very easy. Would you please explain how much important this parameter is, which actually is enjoyed by the perovskite materials or the perovskite solar cells?
Yes, it's interesting because you can place the band gap wherever you want by mixing the anions or by mixing the allied anions or the cations. And well, this is good. This can be good for solar cells, but also for emitter devices like LEDs and things like that. And well, concerning the solar cells, now there are some approaches to produce multi-junction solar cells using only perovskite. So you can have something similar to a multi-junction. So using a perovskite solar cell with a small gap, 1.6 electron volt, which is the minimum, or 2.5 electron volt. And you can stack different solar cells to produce multi-junction solar cells or tandem solar cells.
Thank you very much, Professor. I have received your souvenir, and inshallah, Amir Shafi will carry it and hand it over to you. Good afternoon.
Good afternoon.
Thank you, sir. I consider it a great honor to welcome Dr. Muzaffar, who is currently a professor in UET Texla in Department of Mechanical Engineering. Sir, his teaching and research interests include HVAC and solar thermal air conditioning, energy systems, modeling and optimization, solar thermal collectors, solar PV systems, and nanofluids. He has already published more than 60 impact factor publications in well-reputed international journals, having an impact factor of above 200. Sir.
Assalamu alaikum. Ladies and gentlemen, first of all, I would like to thank Dr. Shajir and his team for giving me this opportunity to present something about solar thermal system. So I know it's very hard, and I think your saturation limit has already been crossed, because it's very difficult to sit whole day and to absorb such a technical and informative discussion. So I will try my level best to keep it as simple as possible, as short as possible. So the topic which I'm going to present today, it's about solar thermal system. From the whole day, I think you are listening about the solar PV systems, and you have already understood this thing, that they are not so efficient. So many things, so many techniques being applied to make them more efficient. So it's time to now talk about solar thermal systems, which are more efficient, and their efficiency is more than 40%. So the main thing which I would like to highlight, it's about the intelligent buildings, and most importantly, that how we can integrate these solar thermal systems with the intelligent buildings. There are so many aspects that you can use the solar thermal system for heating, but most importantly, most importantly, we know that the air conditioning demand is going up. So it's time to focus on the solar air conditioning system so that the more than 50% of the load which we have in summer can be handled by the solar thermal system. So I will talk about some intelligent buildings, then the development of a solar thermal system, because in last so many years, whenever we talk about solar thermal system, everyone says it's doable. But whenever you say that just, okay, it's doable, just show us a tangible system, a real system working under the real condition, but no one has the solution. So we have developed a system under a HEC funded project. So I will show some basics of that system. And one of the key issue which we are facing, it's about the commercialization. So I will discuss that. It's not working. Can I have a pointer? This is slides. It's not working. Okay, the building sector is a very important sector. Normally, we categorize the energy consumption in three sectors: building, transport, and industrial sector. So, building sector holds a very significant amount of energy consumption. You can see it's around the world. It's around the world. You can see it's here's the laser. Yeah. Okay. So it's not going back in. Okay, 35% you can say the share of building in energy consumption, and normally we talk about CO2 footprint, but it's quite high. You can see here. Maybe it's not working. But now we are also talking about the water footprint, because we know that water is becoming quite short. So it's not only CO2, it's also the water footprint which we need to talk about. And another thing, if we just focus on the building sector, then you can see globally as well as in Pakistan, its share is around, in Pakistan specifically, its share is around 40%. But as far as the global perspective is concerned, it's around 20%. In EU, you can see it's around 40%. In US, it's also 40+%. And it's in Pakistan, it's more than that even. So out of this energy share in the building, mainly around 50% it involves HVAC. HVAC means heating, ventilation, and air conditioning. So it's mean that if we focus on this 50% share out of 40, then we can save a lot of energy. So the potential is there, the opportunity is there. So if we intelligently integrate solar thermal system in the building sector, then we can save a lot of energy. As far as Pakistan is concerned, you can see the building share is around 47%. As far as the water consumption in the building sector is concerned, it's 31%, and the CO2 emission which are being generated from the building, it's around 22%. No intelligent buildings. So it's quite common term, and there are different things which we use. Either it's an intelligent building, energy plus building, net zero energy building, green energy buildings. Although if we go in detail, in depth, there is some minor difference, but overall they represent the main domain which is related to the intelligent building. So whenever we are talking about green building, future building, zero energy building, energy plus building, so they all normally they fall under the domain of intelligent building. So intelligent building, you can see we have to focus on the structure, the optimal solution which can be provided in terms of structure, in terms of services, in terms of management, as well as in terms of system. But as far as today's discussion is concerned, I'm going to talk about the system, how you can do it. So the first step is to have a increased energy efficiency, which we can achieve through a efficient building construction. people, they are talking about efficient building envelope, having less heat transfer capabilities or more resistance. I heard that Dr. Nadeem Sheikh, he was talking about some U values of the building. So in Pakistan, we have our building energy codes, and they have defined the U values. U values overall heat transfer coefficient for the buildings. The second is the energy system and the appliances. Of course, you cannot build an intelligent building with inefficient appliances. Operating and maintenance should be appropriate, and the change in the user behavior. So change in user behavior mean that you have to conserve energy. You have to create awareness in the people so that they use energy which is being used in the building intelligently, intelligent in terms of energy conservation. But the second step is more important, that address key energy needs with on-site renewable energy sources. This is the important aspect. So if you are living somewhere in Balochistan, so there's need to focus on the solar system. If you are living in Gilgit-Baltistan, then you may go for a geothermal system, for the water resource system. So it is very important that whenever you are going to construct a building, you have to intelligently decide the efficient energy mix, and this energy mix should involve renewable energy resources. So this is the important thing I'm going to talk about. So first of all, I'm going to give you an overview of the intelligent building which exists around the world. You can see that previously we have a mild or the low growth in the European and US, but as far as the Asia is concerned, South Asia is concerned, now the people, they are talking about intelligent building more. These are a few intelligent buildings around the world, and there are few glimpses which I have just shown you here, because you can see the building which is in the Finland. This building was constructed in 2011, and its energy saving was around 60% as compared to conventional building. Okay, and the building in Singapore, it is also 80% efficient. The building, again, another building in Finland, on your left, you can see it saves around 66% of energy, and the building on your right, it saves around more than 200. So it is not an intelligent building in simple terms, it is an energy plus building. So energy plus building, this building is producing more energy than its consumption. Okay, therefore this percentage is quite high. Another building you can see in Germany, its energy saving is around 76%. In the Luxembourg, it's around 80%. Another building in Norway, you can see these two buildings, they are also saving a significant energies. Another buildings in Bulgaria, you can see in Sofia, as well as in London. So all these buildings, they are integrating 100% renewable energy. So the building I'm showing you here, they integrate 100% renewable. It's not only thermal, of course. It's solar PV, it's solar thermal. Solar thermal is being for the heating purpose, because in European countries, the heating requirement is high as compared to cooling demand. This is a building in Austria. Actually, this building on your left, when I was there for my PhD research, I was sitting on 4th floor of this building. And actually, there's an energy research center in Austria. In 2010, they developed a tech base, and the energy saving of the tech base was 40%. Then in 2011, they developed this energy base, and its energy saving was more than 60%. And when I left Austria in 2013, after my PhD, they developed this future-based building who was saving more than 80% of energy. Okay, and the building on your left, its area was more than 7,000 square meters. It was a 4-story building, and it was using renewables. It was using geothermal, solar thermal panels, and solar PV panels. They were not using any electricity from conventional sources. Another very important aspect, that when we say that European, they are far ahead regarding intelligent building, one of the important aspect is the climate, because we consider that the Pakistan is a very rich country in terms of renewables. If you talk about wind, if you talk about solar, so we have a very optimal blend or a mix of renewables in different regions. So you can see that mainly the intelligent buildings, they are in Europe. And if you compare Pakistan with Europe, Pakistan solar index is around 3 times more than the solar index which we have in Europe. Therefore, if European countries, they can work on that, then why Pakistan cannot? So this is the solar map. You can see that the countries where the solar flux or solar intensity is not so high, but still they are working on that. Another diagram, because this is a very important Köppen climate classification. They also use different methods to classify the whole globe in different climate conditions. So you can see at the middle, we have the Gulf countries. But why we don't find any intelligent building in that region? So it's again, it's a matter of awareness. Although technology exists around the world, what we have to do, we have to transfer that technology to these countries, as well as we can say we have to transfer this technology to Pakistan. This is a comparative analysis of the few intelligent buildings which I have shown you. You can see if we talk about the system, then you will find out solar PV system, integration of a solar thermal system, geothermal system is always there. Okay, in some cases, because that's also a very cost-effective solution, especially when you are using it for the heat pump technology. Now, in the last column, if you see, we have the energy savings. So this is energy savings compared to the conventional building. So if you have developed an intelligent building and you compared it with the conventional building, then this is the percentage of saving that you can get if you intelligently integrate renewable energy system with them. Now, Pakistan. You can also find out some cases of intelligent building in Pakistan. I hope you are familiar with the Green Energy Council in Pakistan. They are working on that. So around 21 buildings they are tracked in Pakistan, and they have the LEED certification. And based on the LEED certification, they are being considered and they are certified as a intelligent energy building. So mainly you can see these buildings, they are in Lahore or few buildings in Karachi. Now, as I said, that the concept of intelligent building system has no meaning without integration of intelligent system. Intelligent system in terms of not only control, but intelligent system in terms of utilization of renewable energy system. The renewable energy system, which I'm going to talk about, it's the air conditioning system, because in Gulf country as well as in Pakistan, the requirements because of global warming and some other factor, everyone is talking about more thermal comfort. It's not, I think it's a basic need of the human, but the efficiency will improve with this if we install air conditioning system in an industry, in a building, in a classroom. So the environment, when the environment will change, when you will provide thermal comfort to the human beings, then their efficiency will increase. So this is not a luxury, it is the basic necessity. So around the world, more than 2,000 systems, air conditioning systems they are installed. Again, I'm talking about solar thermal system, not a solar PV system, because solar PV systems can also be integrated with the conventional air conditioning system, so that you can have a reduction in the power consumption of the panel. You can see in India, 24% of the system they are in India, 12% in Australia, and also in Turkey. We have intelligent systems in terms of air conditioning. As far as their market potential is concerned, we have a significant market potential. There's a certain increase in the growth. You can see 40 to 70% average growth rate is recorded as far as the integration of air conditioning systems with the building is concerned. So it's quite significant. Now, as far as technologies are concerned, as I said, as I mentioned before, that you can also use photovoltaic directly to operate the vapor compression system, but mainly we are talking about the solar thermal system. Of course, when you have to operate solar thermal system, you need a certain operating temperature. So you can see the technologies, they are mainly desiccant system, ejector system, adsorption and chemical reaction. I'm not going into detail. Just I would like to say that the temperature band is very important. But as far as the solar index, the availability of solar index in Pakistan is concerned, you can easily achieve 150. There's no problem with that. The system which I'm going to talk about is the desiccant system, because it has some advantages and its technology is not so much complicated. And there's another reason that I have already worked on this system when I was in Austria. So you can see that the share currently, you can see as far as the global prospect is concerned, the adsorption system has more share as compared to solar desiccant system. And you can see that the air conditioning system, it's not only being used in the building, but it's also being used in the industry as well as in the commercial application, because normally we divide that the building is either it's a residential building or a commercial building. So we have a significant share. So whenever we have integration of solar thermal system, it will not only provide you comfort, it will also reduce CO2 emissions as well. Now you can see Germany is a leading country which has a very good blend of all these technologies. You will find out solar adsorption system, desiccant system, solar PV system, all the systems you can see they are being used in Germany. You can also find out these technologies, how they exist in different countries. It's about the cooling power which you can get from the system. You can see Spain is the leading country as is the cooling power in kilowatt, which you are getting from the solar air conditioning system. This is another diagram which is showing that these systems on the global map, solar map, you can see India is there. Now China is focusing on that. But again, if you just have a look at the Gulf country in the middle of the band, you can see we have a very high solar index, but still the air conditioning system, they are not being installed in those countries. Now let's talk about Pakistan. So why we need to install the system in Pakistan? You can see the solar index. I have just highlighted the location of Texla where we have developed this system. So you can see in summer, the solar index in Texla is around 5 to 5.5. And in Austria, it was around 2 kilowatt hour per square meter per day. So in Texla, it's around 3 times more than that. So if a system can perfectly work in Vienna, then why it cannot be operated in Texla? There's another advantage that normally we say, okay, we have a more heating demand in winter, but in winter condition, we don't have a high solar radiation. But as far as air conditioning is concerned, we have a perfect match in summer, because in summer, we have a more air conditioning, but at the same time, we have the high availability of the solar radiation. So demand and availability of solar radiation, they are in phase with each other. Therefore, it's most viable technology. Now, again, why Pakistan? Our PM, he's talking about so many times that he's going to construct 5 million homes through this Naya Pakistan housing scheme. So there is need to work on renewable energy system. Although in Naya Housing Pakistan scheme, they have given these green building guidelines. So we are expecting that when these buildings, these houses, they will be constructed, they will integrate these renewable energy technologies. Okay. But as far as my target is concerned, you can see at the top, guarantee and interior climate for residents as a comfortable in summer as well as in winter. So if you don't integrate solar thermal system, then how you will ensure that? So I'm going to talk about that aspect only, although there are some other points as well. So solar desiccant air conditioning system, this SOL is for the so. Desiccant is a technology. You can see this will humidify air. At the same time, it will dehumidify air in certain aspect. We have a desiccant wheel, this blue color device you can see. It's a desiccant wheel, and it will it is based on the silica gel. It will just absorb moisture from the air. Then the very key component which you can see in the orange color, it is the evaporator cooler. So when the moisture will be removed from the air, which is the basic requirement of an air conditioning system, then you have to reduce its temperature. But the very important aspect that when the moisture will be absorbed by the silica gel, after attaining its saturation limit, you have to regenerate it. And this regeneration is being achieved from the solar thermal system. This is the basic concept, that you have to provide hot air to the wheel, wheel who has absorbed maximum moisture. And for that, we will use solar thermal collectors, and these solar thermal collectors will provide us the hot air which will be used to regenerate these wheels so that they can absorb again the moisture from the air. The technology, it's eco-friendly. We are using solar thermal system. As I said before, it has a very minimum operating cost, and it is based on the desiccant cooling system, and water footprint is quite low. Why we are using this solid desiccant system? Because its COP is not so bad. It's good, it's acceptable. But the important thing which you can see, that the area required per kilowatt of cooling capacity is quite low as compared to some other technologies. Therefore, I have preferred this system to be used in Pakistan. Now, as I said, the moisture will be absorbed by the silica gel, but you have to reduce temperature. And conventionally, what we are doing, we are using this direct evaporators, direct contact evaporators. But if we use special technology which we have developed, although it's already exists internationally, but we develop at its own by using our local materials. So it's quite efficient. It's a heat and mass exchanger. So this heat and mass exchanger, it will reduce temperature to a comfortable level. This is some pictures, and we have already filed its patent to IPO. So let's hope it will be accepted. And you can see this technology is very simple. We have a dry channels and we have a wet channels. If you have some basics of this thermal technology, then you must know this, that in a conventional desert coolers or this Lahori cooler, we can cool down air up to its wet bulb temperature. But as far as this HMX technology is concerned, you can reduce air temperature up to dew point temperature. So it's very, very good and quite efficient technology. We are working on that. We have developed some systems at the small scale, and you have seen AC, like a tower AC you can see in this hall. So we are also going to fabricate similar kind of structure through this HMX. We have developed many prototypes. Actually, we have developed more than 10 prototypes, and the 14th prototype, we are going to claim it as a patent, because this is the localized technology development. It needs time, and we spent around 2 years on this. So we played with it. We use different materials. We use different flow patterns. So it's complete thermodynamics. I'm not going to discuss it. This is solar thermal system which we have developed. You can see we are just choosing evacuated tube collectors. They are providing us hot water around 90 degrees centigrade, and through that hot water we are achieving air temperature around 70 degrees centigrade, and 70 degrees centigrade is enough to regenerate desiccant wheel, to regenerate silica gel, to make it again possible to absorb moisture from the air. So the other components, you can also see it here. As far as its current operation is concerned, the coefficient of performance which we achieved, it's around 0.6. It's not bad. It's although it's quite low as compared to conventional air conditioning system whose COP is more than 1.5, around 2. But just have a look at the EER, energy efficiency ratio. It's around 6. It's quite good. And the system which we have developed, its cooling capacity is 2.5 ton. It's quite a good solution for domestic application, because normally in domestic application we have 2 rooms, and if we have a system around 2.5 tons of cooling capacity, then it will be enough. Now, the important thing that we have to launch it. We have to launch it as a product. So the first thing, in the competitive analysis, you can see that currently we have the AC, the conventional AC in the market, they are being sold around 1 million units per annum, and the growth is around 5%. The leading brands you can see is higher, having the significant share around 22% than Gree, Orient, Pell, and Dollars. So these are the brands, and we are trying to contact them. And there are, of course, there are so many problems, but we are trying to replace the conventional air conditioning with the solar air conditioning system. So our system is sustainable and environmental friendly. This is one of the core thing, because in the conventional systems, we are using CFCs, although there's improvement in that aspect as well, but still they are not environmental friendly and they are not sustainable. Sustainable mean that if you say that if something is not environmental friendly, you cannot consider it as a sustainable. So the technology which we are going to introduce is a environmental friendly. Of course, it's need very low energy consumption, and as I said, that its size is quite high, almost it's double or 3 times the size of the conventional AC. But if you use localized ducting within a single family home for 2 rooms, then you can efficiently use it. And this has been used around the world. It's not a issue at all. One of the issue is that currently we are using electric heater for its backup. And there's another thing that we can also store energy through this thermal energy storage system. One of the attractive technique is the PCM, the phase change materials. They are also being introduced, and we can make it a solution which can also be done during the night. But I say that if you just use it for an office building, which operates from 9 to 5, so in 9 to 5, we don't have any problem with the solar radiation. So 9 to 5 mean 8 to 9 hours. So if you just apply these systems for 8 to 9 hours, so it's mean out of 24, you are saving 33% of energy. And that 33 is quite significant. Now, there are 2 things. One is the complete AC. The second one is this HMX. And if you just replace this Lahori cooler, which is totally inefficient. Okay, just if you use, but we are trying that we introduce this HMX as a separate product to replace Lahori cooler, and the integration of Desiccant Wheel with this HMX will help us to replace the conventional AC. Okay, so we have so many advantages. We have a direct evaporation in Lahori cooler, but that's not efficient. So as far as the air quality is concerned, we have 5-star with this HMX. Cost, it's quite cost effective, although the Lahori cooler, desert cooler is also good. We have a very good control on the moisture. As I said, there are dry channels and there are wet channels, so moisture is not being added. I think you are familiar that you cannot use this desert cooler in monsoon, where humidity is quite high. You cannot use it for at least 1.5 to 2 months. So if you integrate it with this silica gel kind of technology, then it will be very efficient. Okay, so it's environmental friendly, it's sustainable, energy efficiency ratio is also high, it's not so much complex to produce. Water quality, the water quality in HMX is far more better than the water quality which we have in the desert cooler. The second aspect, which is the holistic view, that what kind of advantages, if we compare it, you can see initial cost is high as far as this desiccant based air conditioning system is concerned. Although it's high, but it's not so high. You can cover it through this low operating cost. Operation cost is quite low. You can see we have 5-star. This is again based on our own understanding. Air quality is quite good. Environmental sustainability, it's quite high for the desiccant cooling system. Payback period is also quite realistic. Electricity consumption is quite low. Thermal comfort is almost comparable. The one of the drawback which just come in our mind and in some people mind, they say that its size is quite high as compared to conventional AC. But as I said, just use some local ducting, then it will be a perfect size. The last thing which I would like to highlight, the commercialization. Someone was talking about what is the role of academia, being a professor, being a teacher, being a whatever you say. I tried my level best to build it. I have some so-called expertise on that. So research has been done. We are trying to have some disclosure agreements. Assessment is perfect. We are getting thermal comfort. There is no problem with that. We are trying to have a good marketing strategy, although I'm not expert in that. But the key issue is the uphill task is the licensing. And I'm open to say that although we have signed a license with a company who is willing to produce this solar AC as a product, but I think because of this pandemic situation, the economic situation of our industry is not so good. So they are reluctant to some extent, and we are hoping that they will help us so that we could launch it. The system which we have produced is just one system. We are hoping to introduce around 50 systems in this year, 100 systems in next year. So we will gradually increase the quantity of the system. And when the quantity of the system will be increased, when we have the mass production, then automatically the overall cost of the system will reduce significantly. So I would like to just conclude that the buildings in Pakistan, they have a significant share. It's 45 plus. But the important thing that these buildings, they should be intelligent. They should be intelligent in terms of construction material. They should be intelligent in terms of surfaces. They should be intelligent in terms of management. And most importantly, they should be intelligent in terms of integration of renewable energy systems. Okay, and solar air conditioning system has the bulk of the load as far as the summer is concerned. So we have to integrate solar air conditioning system, which is the evident solution. HMX is another opportunity which we have developed. One of the important thing is the testing. So we have a very robust kind of testing, and we have already published the findings in terms of thermal comfort. So the thermal comfort is no problem. We can ensure thermal comfort as far as the operation of these system is concerned. But at the last, you can see we need the industrial support, and hopefully we are trying our level best that we will get some industrial support. Because as far as the mass production is concerned, we have to ensure some minimum supply chain, and that supply chain, hopefully it will be developed by few industries. And we are hopeful that we will be able to launch this solar thermal air conditioning soon in Pakistan. Thank you. That's all from my side. So it's open for comments, for questions, whatever you have. Its initial cost is high. It's around 1.5 times. Yeah.
And what about frontier cooling? Because now its price has gone down.
You can also use it. We have actually used it for a thermal jacket, thermal AC jacket. We have used it, but its capacity is quite small. Mean that if you say that we have to use it for example, 5 ton of cooling capacity, 10 ton of cooling capacity, then we need to work on that. We have integrated this pack layer cooler with the jacket, which we have developed, and we are using solar panels with that, the amorphous solar panels with that. So it proved good, but we observed that whenever we have to go for a high capacity of cooling system where the ducting is involved, where the bulk quantity of air, high CFMs are involved. The system which I have designed, it's around 1500 to 2000 CFMs. So what we observed that if we go for the higher CFMs, then we have to build a very bigger system based on this pack layer effect.
I think people are using there because I visited a few weeks ago Hall Road Hot, and the third tier of plates were at many shops.
Yeah, but it's very small quantity. The solution which we have proposed, as I said, it's around 2 to 2.5, but we are targeting it for 10 ton of cooling capacity, for 50 ton of cooling capacity. And it's also very good solution for the pharmaceutical industry because it involves solar desiccant dehumidification, and dehumidification is key element in the pharmaceutical. So this can also be integrated with that. Yeah.
For more than 30 years, I have.
Yeah, it's well established technology.
Cooling is very fast and temperature I think goes to below -10.
Yes, you are right.
And AliExpress is selling.
Yeah, they are selling for this. But again, what is their capacity? Refrigerator with the quarter ton of capacity or half ton of capacity. But if we go for a 5 ton, 10 tons, the system which I work in Vienna, its capacity was more than 200 tons. I don't know. I have not said that. I don't know. I don't know whether it's absorption, desiccant, because these are main three technologies: absorption, adsorption, and desiccant. Absorption is not commercialized yet, but absorption is more common. But absorption technology works under vacuum condition. You have to create severe vacuum condition so that you can boil lithium bromide under certain condition. We tried to work on that, but actually we were unable to build a good structure which could maintain very high level of vacuum. But as far as desiccant is concerned, it is just the working air is air, simple air, and we are just using silica gel for moisture removal. No refrigerant is involved, no ammonia, no lithium chromide, nothing. Sir, you.
Yes, I have one small question. How sustainable is this technology?
In terms of?
In terms of
It's environmental friendly. In terms of life,
in terms of life cycle.
you can use it for more than 20 years. No problem with that. Silica gel is not so expensive.
And
You can recycle it for more than 15,000 hours, 15,000 number of cycles. You can absorb it, then you can regenerate it.
and,
So there's no problem with that.
and you mentioned about 1 million cost
Sorry,
cost
cost of?
this system, for example, 1 ton or 2 ton.
No, conventional is around 1,100,000. This will cost around 2. So its cost is double. But as I said, we are saying its cost will be almost comparable, or it will be around 150,000 when its mass production will start. Okay, economics के अंदर ये rule है कि when you will go for the mass production, cost becomes almost half. But we need some industrial support for the mass production. Sure, sir. Yes. Yes.
So how can you say that, because there should be artificial intelligence involved? If there is
Sure.
artificial intelligence, then how the buildings can be intelligent in terms of?
Of course. But you cannot say that you cannot apply intelligent or IA techniques with the renewable energy systems.
So there should be some intelligence.
Yeah. This is what I said. Intelligent building should be constructed intelligently in terms of material. It should be controlled intelligently. This is what I said. There are 4 key elements. You cannot call a building intelligent if its structure is not intelligent, if its control is not intelligent, if its management is not intelligent, and the last one which I talked about, if its system is not intelligent. So system intelligence is related with the renewable, how you integrate it. Now what we are doing, one of my PhD student, he is working on intelligent predictive control of this air conditioning system based on the machine learning. So he is working on that. So what we did, one of my first student, he developed small prototype, and my second student, she worked on that, and she worked on multiple configuration of desiccant. My third PhD student, he is working on this ML technology. This is model predictive control. This is the model predictive control because we have to intelligently control the system. Let's assume that I know that this system has to maintain a certain load tomorrow, and based on the weather forecast, my system should be tuned few hours before that. He must know that, okay, tomorrow we have a cloudy day, so how I have to operate this system. So we are working on that. So I never said mean that I'm calling a building without its intelligent control. So it's essential element. Anything else? Sure, sir. Who can make it intelligent? We need resources, sir. We need funding. If you are able to provide funding, then we can do it. This system is already integrated with the control. Okay, so it's much better that if you focus on the solar thermal as well, because space heating, space cooling, we know that we have a gas crisis in winter, we have an electricity crisis in summer. So I think the way forward that we focus on the solar panels plus solar thermal, because their efficiency is more than 40%. How much mean that? Because we have a single solution currently, and if someone is willing to have another solution, then he has to pay, as I said, around 200,000. Of course, sir, I don't have any money. Being a professor, I don't have a money. Yeah, because you are end user, so currently you have to pay for that. Thank you very much. Thank you very much. Any question from the audience? Thank you very much.
Now to conclude the session, I will invite Professor. Dr. Muzaffar Ali. Thank you, ladies and gentlemen, for today, and we will join at 9:30 a.m. tomorrow.